not sure who told you all that. That sounds like somebody was spying on me. Well, welcome. I'm glad to be moderating this panel and want to welcome all of you. I'm going to introduce each of you and then have you give your presentations in this order. First, we have Kate Howling. She's a storage engineer with Energy, which is identifies, secures opportunities to add Invenergy's energy storage pipeline of 1,500 megawatts plus worldwide. She started there in 2015 on the operations electrical engineer team. One thing I thought specifically interesting in her bio was that she realized her design experience would be strengthened by field work, and she switched jobs and moved to New Orleans at one point in her career to rehab houses as an electrician. Welcome, Kate. And she got her electrical engineering degree in 2010. Dr. Timothy, well, actually, I'm out of order here, sorry. I practiced this. Dr. Roman Sidortsov is a assistant professor of energy policy at MTU. He's a native of Siberia, and he has a diverse international background as an educator, researcher, consultant, and practicing attorney. He's developed and taught law and policy courses ranging from renewable energy and alternative fuels to administrative law at Vermont Law School. And you know, I graduated from Michigan Tech, so you have a list of some of your classes that you're teaching there, and they're just awesome. I wish I had been there when you were there. Seminar in energy and climate policy, energy security and justice. Anyways, pretty cool. So welcome. And Dr. Timothy Scarlett, Associate Professor of Archaeology and Anthropology at MTU. He caught the archaeology bug as a 17-year-old high school student, and he dedicated his life thereafter to archaeological study of American history. He has degrees in anthropology and/or archaeology from a variety of institutions, and he joined Michigan Tech as an associate professor, or as a professor in the archaeology program in the Department of Social Sciences at Michigan Tech in 2001. Welcome. Catherine Peritic, Director of Engineering at NR Store, Inc. It's a leading energy storage project developer, where Catherine leads the technical work to develop and build energy storage systems for the electric grid. She works with technologies from flywheels to batteries to microgrids, all with the goal of increasing renewable energy penetration on the electric grid efficiently and cost effectively. And one really interesting thing on her bio, she was a reliability engineer for the Mars rover Curiosity during her time at NASA's Jet Propulsion Laboratory. Nate Washburn, project manager of battery storage and unmanned aircraft systems with Consumers Energy. Nate has been with Consumers Energy for more than 10 years as the program manager of the unmanned aircraft systems, which is drones, and battery storage programs at Consumers Energy. He enjoys cultivating innovative solutions in the areas of safety and efficiency. He previously worked in lines engineering and substation engineering. He enjoys spending time with family, traveling, and renovating his home. So please join me in thanking and welcoming all these people. And Kate, you want to start off?
Hello, everybody. Thanks, Pat. I need some green smoothie recipes, so hoping you can help me out. Okay, cool. I love Brussels sprouts. Okay, so my name is Kate Howling. I work for Invenergy. So for those of you who are not familiar, Invenergy is a privately held organization. We develop, own, and operate renewable energy farms. Internationally now, we focus in North America. We're North America's largest privately held wind owner and operator. And we actually recently announced the commercial operation date of our, I think, Michigan's biggest wind farm. It was a build transfer with DTE that happened within the last month or so. So, you know, we're kind of a smaller company trying to play with the big boys and trying to be out here making some money. I have been with Invenergy for 4 years. So I joined as operations electrical engineer, so I was focusing on the operations of our existing battery storage projects, which you see on the board right now. So I have 4 years of experience operating battery projects, but recently, the past year or so, I was doing development also. So I focus on procuring new projects in our pipeline, and then we have kind of we work on developing and constructing these projects hand in hand with other teams at our company. So I won't go through all of these projects, but I did want to highlight a few on here. Most of these operate in PJM's fast frequency regulation market, which Scott had explained earlier today. So to give a quick overview of that, basically there's differences between load and generation on the grid, which causes disturbances in frequency. Batteries can help be immediately dispatchable to help meet that. So we can charge if there's too much generation on the grid. We can discharge if there's not enough. So most of these projects participate in the PJM market. In 2012, we were early adopters with a smaller project, 1.5 megawatts, there at our co-located with a wind site in Illinois called Grand Ridge. Another project I want to highlight is the project in Iowa. That was a build transfer we recently completed with Mid-American, which is a utility in Iowa. It's a kind of pilot project for them. But what I really want to highlight is that project was really fast-paced, and from the moment we executed our contract with Mid-American for the build transfer, less than 4 months later, we were operating. So it was extremely quick, and I want to highlight that because it highlights sort of how, I'm going to say easy. It wasn't like it was easy, but the construction scope for battery projects, it honestly is really small. There was 1 full week of construction for that project. The rest of that was delivery times, waiting for delivery times, and commissioning. So these projects really, they're not rocket science to sort of onboard like that. We have over 700 megawatt hours either awarded or contracted in our pipeline, and I will highlight some of that today. We continue our track record of innovation. We have been recognized for that. In 2015, we won the Power Gen Project of the Year for our big 31 megawatt Grand Ridge project, which again it's co-located with our wind farm, as you can see, and that's participating in the PJM market. So I wanted to go through Energy Storage 101. Jeremy did an amazing job this morning doing this, so I'm going to breeze through these slides. But in its simplest form or simplest definition, energy storage basically stores electricity to be used at a later time. 3 words that I like to use to explain energy storage, and I'll use them again and again in this presentation, is modular, scalable, flexible. Energy storage can be placed anywhere from as a transmission asset on the transmission line. A lot of our existing battery projects are co-located with our wind sites, which are on their transmission assets, all the way down to distribution. So the Mid-American project that we have, I think that's a 12 kV line that we tap into. So, there's a lot of opportunity and optionality for energy storage projects. I don't know if this industry has eclipsed this yet, but if we haven't, we will soon to eclipse 1 gigawatt of installed energy storage in North America. There's estimates that there will be 3.9 gigawatts by 2023, and that represents a 4.6 billions and billions dollar market. What's driving that is decrease of cost. So since 2011, there has been an 80%, the price for energy storage has decreased 80%. That's largely driven by electric vehicles. So, internationally, Asia, Europe, America, as we continue, as the demand for electric vehicles, buses, and cars continues to rise, we're just going to keep enjoying a downward price curve in the energy storage that's used in those vehicles that we also use in stationary storage. So, I think sometimes it helps to visualize this. This might be, oversimplified for a lot of the people in this room, but we talk a lot about kilowatts, kilowatt hours, and this visual kind of helps explain that. So if you think about an energy storage resource as a tank, the size of the tank is how many megawatt hours you have in your battery. How much can you fill that tank? The faucet represents the power. How quickly, if you open that faucet all the way, how quickly can all of that water pour out? That represents your inverter size in a real energy storage project, which represents your power, your kilowatts. So you might have a huge tank. You might have a huge tank that can store 10 megawatt hours of electricity. But if you only have a tiny little faucet, like a 2 megawatt faucet, you would have a 2 megawatt, 10 megawatt hour resource. So you can run 2 megawatts for 5 hours. It could be swapped the other way. You could have, a pretty small tank and a giant faucet. You can run 31.5 megawatts for 30 minutes. That's exactly what our resources do in the PJM market. So I wanted to go through and highlight three different projects that we have, and specifically focus on some of the drivers for those projects and why they came to existence. So this is our Grand Ridge Energy Storage Site. You might recognize that picture because Scott also used it in his presentation. So this, again, is participating in the PJM market. So the driver for this was really that the market opened up. It was a lucrative market. We joined in. We have about 65 megawatts that are participating in the PJM market, and it's been pretty lucrative and beneficial for us, even though we've been trying to handle some of the market changes which affect the the capacity of our existing storage assets. So all of our PJM resources are co-located with wind sites. So what that enabled us to do is save on some construction costs. We don't have to build a substation. We just use the existing substation and add a feeder. So Scott mentioned why this market was so beneficial for PJM. The sort of immediate nature of batteries allows them to dispatch immediately. I think that he said 300 megawatts is what's in the market for this fast regulation market. It allows them to dispatch that immediately, so they have to procure less peakers to do the same exact job because storage basically doesn't have a ramp rate. So they were able to save a lot of money because they are procuring immediate resources to the tune of $90 million. This project I really wanted to focus on. We, Invenergy, recently announced that we got a PPA project with Arizona Public Service, or APS. The driver for this was really that there was a moratorium from the PUC on thermal peakers for APS. So what they incentivize basically is for APS to diversify their peaker generation. It doesn't have to be all thermal. We can also have some batteries in there, like this one. So many peakers nationwide, and I think especially here in the Midwest, can tend to operate less than 400 hours a year. Not very high capacity factor. Energy storage is a cost-effective alternative, especially when you consider all the other services that batteries can provide. APS basically released a request for proposal for this project. We were competing against many other companies. That's kind of how this project came to be. We executed it fairly recently, executed the contract. And I think the thing that makes me the most proud of this project is that as developers, we talk a lot about the flexibility of storage. We can do anything, like voltage regulation, we got it. Frequency response, we can do that. Peaker, yep, we can do that. But with this project, we really had to put our money where our mouth is, and it's one thing to say these things, and it's another thing to have a contract in front of you when you have to contract it all. So this truly represents, that's the stackable functions of battery storage. These PPAs really represent that in real life. They are now. This is the reality of sort of the flexibility and the future of these of peakers and assets like energy storage that can charge and discharge and perform many different services to the grid. So I think I'm really proud this project. We executed it in a very, very short amount of time. The PPA structure for energy storage is not what you frequently see for for existing battery storage projects. It's usually market-driven like PJM or build transfer. It's what a lot of what's going on in California. A lot of them are build transfers. So, I think as the industry continues to mature, we're going to see more and more of PPAs like this. And I think, APS, to their credit, is really paving the way for a lot of this because, I think they have procurement targets, and this will not be the only PPA that they see. And I think that this will be, a format that is replicated in other states as well. So the last project I wanted to focus on is a project in New York that hasn't been publicly announced, so I have to speak a little mysteriously about it. This is it's kind of a two-part project. We have part of it is just a peak shaving energy storage system. I think it's only it's small. It's maybe around like 1 or 2 megawatts for 4 hours. The other part that's they're co-located. It's a microgrid project. That's actually a much larger project. I think it's a maybe 7-hour project that is closer to 10 to 20 megawatts. So it's answering sort of two different needs for this distribution utility. The driver for this was something called Reforming the Energy Vision, or REV. This actually predates storage mandates in New York that I'm sure you're aware of. The REV was developed by the Public Service Commission and different utilities and agencies in New York when the governor tasked those agencies to come up with a plan to increase reliability and to consider non-wireless alternatives, or NWA. So, as you know, there's a number of states that are in the process or have already then gone on to create energy storage mandates. New York is one of them. So is Arizona, California, Massachusetts, New Jersey. Nitsan did a great job highlighting a lot of these. So, the driver here really came from the governor, came from the government, came from the, commission devising and guiding the utilities on how to achieve what was set out in what the governor had, tasked them with. One thing I want to point out is that New York's study in the energy storage roadmap found that storage investment will improve reliability and also create 30,000 jobs, which is pretty significant. And another sort of driver that we don't really talk too much about today, but it's tangible, and that has a lasting influence on the communities that we develop these projects in. So, like I said, we have there's kind of two different projects here, and really what this is it's really just a transmission and distribution deferral project. So there was a large transformer that this utility wanted to kind of put off upgrading, and as an alternative, they came up with a battery storage project. So that's all from me. I'm looking forward to hearing the other presenters here and taking your questions.
Okay. Is this?
Oh.
My colleagues, okay.
Wait, here, you know what? You can do that.
I'm going to do that.
Okay.
Good afternoon. My name is Roman Sidortsov, and I'm here to talk about our current project. And our project is at the stage when I have more personally questions than answers. So hopefully, if you have any questions, I'd be able to answer them. But that's the fine print that I want to make not so fine. So thank you very much. I would like to thank the organizers for inviting us here to talk about this project, even though we only have very, very preliminary results to highlight. And I will share this presentation with my colleague, Dr. Tim Scarlett. So here's what I would like to cover today. So I would like to present the idea, the inspiration, if you would, for this project. Tim will then dive deep into the economic, social, and cultural reasons for doing, or at least trying to do, something that we're trying to do. And then I will highlight the sort of the overall concept behind this project that extends well beyond just engineering and economics, and encompasses things like economic development and cultural heritage, etc. So then I'll briefly introduce this project as it is funded at the time, and we'll also say a few things about what we would like to do and what we're seeking funding to do next. So this is how this project started. It started with me running up that hill. Well, here I was really snowshoeing up that hill. This is the hill that leads up to Quincy Mine, depicted in the center of your screen. That's my dog waiting for me, hopefully listening. And as I would run up that hill with no problem, for those who, yes, that's my kind of audience. So I would start thinking, right? So like, it's a pretty steep hill. Like, why? What's up with this elevation, and what can be done productive with this elevation, especially given the fact that I'm actually running on the top of a shaft after shaft after shaft after shaft of the Quincy mine. So, and I took this idea of I knew about pump storage. I introduced it to my students every year, sometimes twice a year. And I took this idea to Tim, and I shared that with him, so we started brainstorming. So this is how the idea was to potentially, thank you. All right. So the idea was conceived, and the idea was to potentially try to figure out if we can place pump storage or assess whether the pump storage facility can be placed inside a mine akin to the mine depicted here. So there were other drivers, and some of them that contributed to the conceiving this project. We live in a basically a snow globe in the Upper Peninsula. So people would like in the community to see more renewable distributed sources, but we also have challenges. We do have the weather. People who would like to resist the weather, for example, and install geothermal pumps, they cannot because of this. And what you see here is the electricity rates in the Upper Peninsula from the paper that was written and published by my colleagues at Michigan Tech. So the rates are high, the second highest in the nation after the state of Hawaii. So, a lot of technologies that might make sense economically in other parts of the United States or in the other parts of Michigan, that would actually make sense, that we actually can reach this grid parity. So we also have some seasonal uses. And on the chart below, and this PowerPoint will be available, you will see the effective rates for seasonal users. They can reach as high as 50 cents per kilowatt hour. So my rate is, the data is from 2013, but my current rate is around, I think, 23, 24 effective rate per kilowatt hour. So what it effectively does, it impacts of what people can do, what businesses can do, what kind of installations, what kind of things people can afford in their houses. So it does impact the overall well-being, it does impact overall economic development, etc. So I said that the idea sort of came up as I was running up the hill. I am not going to assert that I came up with this idea. It just sort of popped into my head. As a matter of fact, there have been attempts to utilize underground facilities for this particular purpose. There have been attempts in the United States. I don't think there was a single commercially successful underground hydro pump storage facility in the United States, but there is one that is partially underground in Wales, United Kingdom, called the Norwich Power Station. So what it is basically a reservoir is located above the ground, but a lot of the infrastructure is located inside a mountain. And the reason for that, the main reason for that, is because the power station, the power plant, is located in the Snowdonia National Park. And if you are of Welsh heritage, you would probably understand that that means a lot. It's one of the treasures of the Welsh people. So this is what Quincy Mine looks like, dry and flooded levels. So the idea, again, is nothing new. You just basically take a pump storage facility and you place it inside the mine. You place it on the upper reservoir. When you have excess capacity, excess energy in the system, you basically fill up the upper reservoir. When you have the demand, you run it down. So, I mean, works as basically a regular hydro pump storage facility. What it has in terms of additional benefits is that it has a nearly constant temperature of the water. So you don't have to deal with things like ice, snow. You don't have to deal with things like the elements, those kind of things, right? So you operate sort of, in almost a constant temperature. So,
Hey, Roman. Just for people who are trying to imagine this in your head, that mine is 9,000 feet deep and 5,000 feet wide or long, and anywhere from several 10 to several hundred feet wide. So you're looking at something that is 1.5 miles deep, 1 mile long. It's a big battery. The temperatures range from about 40 degrees, 38 degrees at the upper flooded levels, down to 100, 110 degrees water at the bottom levels.
so back to you, Tim.
Yeah.
for
Oh,
your
thanks,
part.
Roman. We're gonna bounce back and forth, and I'm sorry to the camera operator, but I want to draw these people in a little bit because I've been feeling like you're neglected. So I'm going to stand over here, and I'm going to speak just sort of really briefly and maybe answer your question of why an archaeologist is here. When Roman came to talk to me, he came to see me because I do a lot of mining archaeology. I work a lot with abandoned and historic mines, with industrial communities and post-mining communities in these studies. And we quickly in our conversations got really very excited. I want you to understand, who's been to the Upper Peninsula? I know there's some Michigan Tech alums that think, wow, excellent. Okay, so these mines are all industrial resource frontier communities. They were created by companies to organize industrial scale production, meaning from nothing, elaborate infrastructures were built to support industrial mining. It's cosmopolitan urbanism on the resource frontier. What that meant was that the community around the mines, very close, and that those mines over the lifespan of their operation often were the first electrical generators that pumped electricity out to their communities, providing the miners who were their staff with energy services. So I need you to keep in mind this cosmopolitan frontier with intensely multicultural communities, lots of immigrants in these communities forming the work body. Next slide, please. Actually, maybe, Roman, you could give me the clicker, because I'll just flip through some.
I choose service. I choose service. Ooh. And I already screwed up.
That's okay. And as you think about that, these communities, as they shift into the post-mining environment, the post-mining situation, like most post-industrial communities in these economic transitions, they suffer from economic recession or depression. They need environmental remediations, and they need cultural renewal, cultural energy. Generally, you could imagine that in your head. Communities come to schools like ours, get college degrees, and then they leave, and they don't come back, right? So the communities, if you're thinking like a city manager, these are their concerns, which connect to what Ron was talking about: high utility costs, high electric, prohibitive barriers to communities, not just economic, it's the value, right? Our communities have experimented with a wide range of ways of reusing these facilities as assets instead of thinking them as liabilities. Parks, ride a mountain bike race through a mine underground with a light on your head. Some of them are national parks, some of them are owned by state, some of them are owned by private organizations. There's a wide array of experiments happening, trying to use these as assets. And what we are suggesting in this design, as we began talking about it, we realized how compatible our vision was with all of these other uses. Because an underground pump hydro storage facility can become and can remain operated as a park on the surface, as a historic site that's the center of the community's identity. It can still be bat habitat as a reclaimed mine. All of these things, if you design well, can be included in these designs. Now, we started looking around for partners. We were thinking about different mines. We were thinking about Quincy initially just to get started. But we eventually found partners in the city of Negaunee, in the Iron Ranges of Upper Michigan, and with WPPI Energy. And we're very grateful for their involvement. This is the Mather mine, which is one of the mines in the area of Negaunee. Negaunee, Ishpeming, and Marquette being iron mining regions. And like our story earlier, this is the, whoop. There we go. This is the Mather mine today. It's the Negaunee High School. Underneath this high school is a mine battery, like we were talking about, was it Jackson Park as an example, where these students need training in technical skills. They need jobs that are high-paying jobs when they get out. The community is looking for energy investment. They're looking for all of these things that are on their radar. Everyone is so excited about this project that we got a grant. That's all we've done so far, is to get a grant. And we've attracted national and international attention in thinking about what this means. And as you think about it, these are the mines in the United States, all mines in the mineral service database. And you are trying to envision service areas and different kinds of things. These are the metal mines, so they're more likely to be more substantial, not like gravel quarries and things like that. And to zoom in on our region, again, these are all mines, and these are metal mines. To give you an idea of the potential widespread application of these technologies. And more to the point, in the work that we do at Michigan Tech, what we really are good at is creating interdisciplinary or even transdisciplinary learning environments for student teams to design things. And one of the ways that we've envisioned this project, we started to think about moving forward, is to look at and think about the ways in which these projects can articulate with all of these other things. And I bring that up because most of you in this room, I'm going to go out on a limb, think of historic preservation law, like the National Historic Preservation Act or the NEPA, as a hindrance to what you do day to day. And I'm going to tell you that you're wrong, because the historic preservationists are your allies in this. The communities are your allies. We're not going to go through the details of how Section 106 review happens or the NEPA process happens for consultation. But if you skip out of even the legal requirements of how these systems work for when these laws apply and start the consultation process at an early period. In the design of these projects, we've worked with many different heritage sites and thinking about articulating with the public with industrial history sites. These are some of our students helping a community organization giving tours at the site of the Quincy Smelter. This is us at the site of the Cliff Mine out in Keweenaw County. On this project, we were excavating on this project at this site, and word got out. We opened up the site for people to come visit us. And to make a long story short, somewhere between 1% and 3% of the entire population within a 4-hour round trip drive came to visit us and see you and talk. And they stayed for hours. And not one person in all of those hours yelled at me. How many of you have been to a charrette or a review meeting where you didn't get yelled at? Because they care. And they're interested to talk about these possibilities if you design the projects and thinking of ways to help solve community problems, right? Thank you, Roman. Back to you.
Thank you, Tim. Back to me. So I was wondering if you could help me with the slides, please. All right. Okay. Well, I will self-help. I'll indulge in self-help. So again, as I was going through sort of, again, I'm running up that really great actually trail. It's very steep, but it's very rewarding, especially if you get on top of it. I started thinking as a former, actually, a lot of practice trying to build so when I practiced law, I did a little bit of energy facility permitting. And I'm thinking about this sort of idea, and I'm thinking about it in terms of the someone who would want to permit something like this. I knew that permitting a regular, conventional hydro pump storage facility is near impossible, right? So you do have site restrictions. Elevation apparently is not available, and waterfronts are not available in the PJM territory, for example. And to permit something like this, it's just, I remember one of my professors was someone who actually almost made a career by opposing pump storage facilities on environmental grounds. And I'm thinking about it as someone who has done permitting, and I'm thinking about every single sort of a soft cost saving measure associated with sites, right? So you do have a site that has normally property rights secured, you have your easement in place, you have normally interconnected site. Those are large industrial users. They actually have wires coming to them. So all of that is in one place. While there are, a lot of them are brownfield sites, there is some contamination, but that's not necessarily a bad thing if you want to develop it. So, so the overall concept for this project and the project, hopefully the next steps, is basically based upon the conversion of a community that is burdened by its post-industrial past to a community that is thriving because of its mining post-industrial past, with the idea of the energy transition. So you take those liabilities, you take those barriers to energy transition, and you flip them and try to utilize them as opportunities and as assets. For example, you have an environmental problem with mine water quality, right? So while you build a facility like this, it can double up as a mine water quality control facility. So you do have, say, policy, legal, and regulatory consequences of being considered a brownfield status. While if you put in remediation, you do have circle liability exception, etc. So, but the relationship, so, and sort of I've outlined some of the relationship. The relationship is not only linear. So we go through things like, all right, so it's your remoteness currently in the UP is a problem if you are a community like this because of the line losses, hence the service charges, et cetera, right? But if you do become sort of this giant battery or in the middle of basically a service territory, you can become a center of that would be using it, right? So you will become a resource that distributed energy resource providers can utilize. So that will absolutely impact the revenue sort of situation with those municipalities that do not get much tax revenue. So that is the idea, that is the overall concept of this project. Now, very quickly about the project as funded. So that's the name of the project. I'm not gonna read it out loud. We've been funded by the Sloan Foundation. Very, very grateful for them for this opportunity. I spoke to the program director. He was really excited about it. He said, yeah, this is a nutty idea, but hey, you know, this is a really cool idea at the same time. So they gave us a little bit of money to do this, what they call is a landscaping or pilot study. So duration for 2 years, but we plan to complete the study this year, predominantly this summer where things are going to take place. So a couple of facts about our team. Here's our team members. I'm by far the least decorated doctor professor on the roster, but I'm leading this project. So as you will see, because Michigan Tech is not a very large university, we only have what 7,000 over 7,000 students, that enables us to assemble this kind of teams very, very quickly. I can give a call to the next building and we can have a meeting, project meeting the next week. So here's everyone who's represented here and the different types of expertise that is involved in this particular project. And again, a special shout out to Nate Hevron, the manager of the city of Negaunee, Brett Niemi from WPPI, who they promised us data, and also Brad Barnett, our alum from Wuppertal, to look at, even though Wuppertal is not in the territory, Negaunee is not in the Wuppertal territory, still his expertise in local economic development is invaluable in this project. So here are our tasks. So we're going to be looking at the technical economic opportunities and barriers. We're going to take sort of this sweeping look at sort of an overall potential, as Tim mentioned to you, sort of to put a number on those dots, right? So we're talking about 170,000, 260,000 legacy mines in the U.S. Most of them are not going to be suitable. I can tell you from right now, because some are not structurally sound, some are not designed or cannot be used because of their geology. Some are in the places where you don't want really to do storage, but there will be quite a few, and in the region near you that will be suitable. I am certain about that. So, and we'll do absolutely further studies to determine that. So the engineers are working at basically looking at modeling how to place a hydroelectric turbine inside the mine, how to ensure that it's a structurally sound reservoir, how to ensure how to grout it, to make sure that the upper reservoir supports that, all that water. So water, legal and regulatory opportunities and barriers, that's yours truly. So I'll be spending about 2 weeks on my computer in Westlaw. So that's what I'm going to be doing. So water quality issues and barriers and opportunities for mine control, that was one of the things that was specifically requested. And social opportunities and barriers for adoption and community engagement, and in particular opportunities for elevating energy property, because in the UP we are energy poor. Project outputs, obviously we're going to do a report, but we've pledged that the report will not have this academic mumbo jumbo, but actually be accessible to various audiences. We'll save the academic mumbo jumbo for academic publications. That's what academics do. Student projects, I have currently 6 students working on this project. I described it, I didn't even think about it when I started teaching my energy transitions class, but I said, well, you need to do a class project, and 6 students responded. So the teams of 2 working on everything from legal status for brownfield status to basically the structural integrity of the upper sort of the upper level of the mine. So I'm going them and taking them on a field trip. As part of this project. I know that Tim has students who are working on this as a class project as well. And we're going to do a transdisciplinary concluding event where we would be delighted to see some of you announce our results and hopefully forge some partnerships. So very quickly, what do we want to do next? Well, be bold or go home, or drive home in our case. So we would like to do a national-wide assessment. So there are 5 modules: technological, environmental, policy, legal and regulatory, socioeconomic, political, geographic. So we would like to be going deep and looking at it, doing additional modeling, sort of see what kind of technologies can work. We also would like to go a little bit wider and see what other technologies, such as compressed air, might be suitable for these kind of sites. So we're going to try to do beyond water quality for the environmental module, look at soil contamination, those kind of things, the way to remediate them. So for the MyPet project, I will be doing a 50-state survey and looking into the federal and some local issues in depth as well. Socioeconomic, we would like to do a national-wide survey of mayors, city managers, etc., as well as to do at least three in-depth case studies where we can actually engage with communities. So, and geographic, obviously we'll need to, Tim will be leading this module, hopefully, to look, gather historic data, mine maps and whatnot, so sort of put it all together, working closely with the geologists, sort of to determine the general sort of geological characteristics of mine types. Our preliminary sort of look at it indicates that their mines are different, but there are types of mines, so there is a way to sort of crunch this data and come up with typologies and in terms of the site suitability. And we would like to come up with a GIS tool that would actually put this whole thing on the map and will map out the most suitable, the least suitable sites, so etc. So we are, this is where we're headed. We would love to collaborate. I came, before I joined academia, I had a full career, and I really love doing applied research. So, and my colleagues thrive to do the same. So we would love to engage with many industry actors, government actors as we can, because we really would like to find out whether we can actually utilize this resource that is currently a liability, but in our opinion, can become a productive asset. So we will update you on Twitter if you'd like to follow us, and thank you very much.
Thank you.
Okay, first of all, I just want to say how thrilled I am to be in a room this large of people who want to talk about energy storage. This is so exciting to me. I have been in energy storage in some capacity or another since 2012. Can anybody else say that? 2012? Isn't this amazing? We have a full room of people who want to talk about energy storage. And it really is the future. This really is, I believe, where energy is going, where our grid is going, where technology is going. So right now, I'm with a company called EnerStore. We're an energy storage project developer. We're actually based out of Canada. I bet most of you in here have not heard of us. We actually are, believe it or not, a leading project developer in Canada, but we haven't done a lot in the US yet. And we're looking for that to change. So that's why we're here, why we're starting to get involved in Michigan, why we're starting to get involved in the US. So talking about some practical applications. So my company, founded in 2012, we have a lot of strategic partners. So we have agreements with technology suppliers, which I'll talk about, with funders, and with other organizations that are supporting our technology project development. We have a very diverse portfolio of energy storage technologies, possibly the most diverse. I'm not entirely sure if that's true or not. But we do a lot on the utility side. So we have a flywheel project. We have the first commercial flywheel project in Canada. It's 2 megawatts. It's located in Minto, Ontario. And we're almost finished building the largest and only contracted fuel-free compressed air energy storage project in the world, which is only 2 megawatts, but it's the first. Then we have also over 100 megawatts of behind-the-meter battery projects that are contracted in Ontario, and we're also a distributor of the Tesla Powerwall in Canada. So we're all over the spectrum in terms of energy storage. So Jeremy had this exact same slide up earlier today. But I do think it really describes the trajectory of energy storage in the country right now. Back from 2012, there is not a lot of storage actually being developed back then. And you can see that it's just projected to keep expanding. And as I heard very recently on a story about energy storage, all of the projections have been wrong up to this point. Every year, the DOE or anybody who's putting together these energy storage projections puts a plot like this together. The next year, they have to go and revise that to be even larger. So those error bands that they've been putting on these are actually not even big enough yet. So this is a fairly recent one. This is from I think it was from 2018, late in 2018. So this one, we'll see if that trend continues, if this ends up having to be expanded even further. And then this is a big part of the reason why. Another thing that Jeremy touched on and a few of the other presenters today have touched on is the declining costs of storage to this date. This is batteries in particular. So this is for lithium-ion batteries that's being shown on the screen right now. So battery costs falling more than 15% per year. A 5-year drop of more than 50%. And this actually does include all of the balance of system. So this is both cell cost plus balance of system plus all of the soft costs, so customer acquisition, development, interconnection, overhead, as well as the EPC, the engineer, procure, construct costs. So including all of that, the costs have just fallen so dramatically. This is a really interesting slide, and if these are going to be distributed later, I think that this is if you're fairly new to energy storage, I think this one's it's really telling about the various areas and benefits that energy storage can provide to different types of customers, and also just the different types of storage in general. So broken down into three main categories. So customer services, so that's mostly behind the meter in the orange there. ISO services, so grid services, that's the arbitrage that has been talked about, frequency regulation, black start, reserves, and also utility services, so more on the transmission, distribution, grid side. But there really are a ton of different applications for energy storage that have the ability, that energy storage has the ability to fulfill. So all storage is not equal. Storage cost and duration definitely does matter when you're matching a grid storage or any type of storage to an application. So we're technology agnostic. We are just an energy storage project developer. We develop lots of different types of energy storage. So you'll take an opportunity, take a need, a grid storage need, and then match the right technology to that. Grid storage technologies come in many, many different flavors, many different sizes, many different durations, different cost profiles. Some are expensive on a dollar per kilowatt basis, but are cheap on a dollar per kilowatt hour basis, and some are the reverse. So lithium-ion batteries don't just fit every application. Flywheels don't fit every application. You have to look at the specific need, the specific value proposition, and then fit the right storage technology to that. So for example, on the plot that's on the screen right now, the one on the left, that shows a bulk energy storage application. So that would be something that would be much longer duration, like maybe flow battery or compressed air energy storage, where you're taking some of that excess renewable energy, surplus electricity, storing it, and then filling in the load profile. Whereas on the right, this is more of a frequency regulation application. So a flywheel would be good for this application, or maybe a capacitor, or maybe a lithium-ion battery. In Venergy, you've got some of those lithium-ion batteries that do exactly that right there. You have to find the right technology for the application that you're trying to fulfill. So we have talked a lot about batteries today, although I am really impressed by the variety of technologies that people have been talking about today. I was actually coming in here expecting this to be a lithium-ion battery conference, which is what most energy storage conferences are that you go to. So I came in saying, I'm going to talk about the other things. I'm going to talk about the non-battery things. But I think there's been a really good representation of all the different types of energy storage out there today. But I'm still going to talk about the non-battery ones. So this is our flywheel project. So this is a high power, low duration, low energy application. So this was the first contracted facility in Canada. It's 2 megawatts. It's been operating since 2014 in a commercial capacity. So it has a contract with the Ontario Independent Electricity System Operator, and so it's two megawatts, but it's only 500 kilowatt hours, so 15-minute duration. It doesn't discharge for very long, but it gets a signal from the grid every 4 seconds to change, either generate or be a load, generate, be a load. And it's been operating really well. So this is what it looks like. That's the building up there in the upper left, the exterior. It's just a very boring looking, large building. And on the inside, you actually can't see too much. The flywheels are underground. So you can see those are the circles that are on the right of that picture. Those are big underground concrete vaults. So the floor goes down underground a few meters. It's solid concrete, and then the flywheels are in there. The flywheels, this is a temporal flywheel technology. So these are steel flywheels. So they're high mass, low speed. They're still fast, but they're the lower speed. They're high mass flywheels. So we've got 10 of those underground vaults there in that picture, and that added up all together, that equals a 2 megawatt facility. And then our other interesting project is our fuel-free compressed air energy storage project. So this is the one that I'm working on really closely right now. It's located out in Goderich, Ontario. It's right on Lake Huron. It's a really, really beautiful little town. In 2015, we got a contract, again through the Ontario Independent Electricity System Operator, who wanted to procure energy storage. And we bid in a 1.75 megawatt, 4-hour compressed air energy storage project and won that RFP. So it's still under construction right now. Hydrostore is the technology provider. So they're actually the inventor of the energy storage technology. It's built on an underground salt mine. So Compass Minerals is a salt manufacturer. So we took the old void that had been mined out. They sold all the salt as table salt, and we're using that unused void underground to store compressed air in the form of to store energy in the form of compressed air. We're also paired with the University of Waterloo to do some research on the project, and it's contracted to the Independent Electricity System Operator. We're almost finished construction. It'll be online next quarter. So this is kind of what it looks like. I wanted to give a really brief overview, a picture of what compressed air energy storage technology looks like, because it is one of the more niche technologies out there that not a lot of people have worked with before, but it is super simple. It is as simple as you just take a big compressor, similar to the one that probably lots of you have in your garage. You turn it on, so you have a motor, runs that compressor, you take that compressed air, you have to cool it down first. You store that heat, this is what makes it fuel-free, you store that heat in a big water tank, essentially, on the surface, and then store the cooled compressed air in that big underground cavern. And then when you want to produce electricity, you let a little bit of that air out, warm it back up with the warm water that's stored on the surface, and let it turn a turbine that turns a generator and produces electricity. It's a really, really simple concept, which is and it's a really easy to understand mechanical concept. And this is what it looks like. So this is our project. This is actually just a rendering of what it'll look like when it's finished. Right now it just looks like a big construction site. I thought this picture was prettier. The one on the left is, that's our actual compressor and expander unit that's inside our building right now. So it's pretty exciting. It's becoming really real. So just in conclusion, I'll finish up pretty quickly here. So the benefits of energy storage, we really do believe that they're key to building a low carbon economy, and we believe that this trend of where the world is going right now with more renewables, more variable generation, energy storage really is necessary for the electrical grid. And that is exactly what we're seeing. As a project developer, we see more and more of this need for storage to support our grid. So and also working with fuel-free technology, whether it's compressed air, whether it's flywheels, whether it's batteries, can eliminate the need for some of the greenhouse gas emitting infrastructure that we have on the system right now. And then, some stats for how much a large system like this can actually benefit the grid, greenhouse gas savings, and this has been independently verified. So for some projects that we're looking at in the future, 100 megawatt, 8-hour fuel-free compressed air energy storage facility can provide 2.5 million tons of CO2 equivalent reduction, so equivalent to removing about 50,000 cars from the road for 10 years. So it really does make a big difference, and we really do believe, and we see in real time, firsthand, the scaling up of this technology and the desire and the need for these energy storage technologies, and we're really excited about the future of energy storage, and excited that we have all of these people in this room right now who want to talk about this, learn about this, and see how energy storage can benefit whatever part of the infrastructure that you guys are all working on right now, or whatever part of the legislature, or whatever you're working on, how energy storage fits into that. It's a really exciting place to be, and thanks so much for having me and getting to talk about energy storage.
I'll go ahead and get started while they're queuing up the next slides here. So Consumers Energy, our storage story, specifically battery storage, not Ludington, started really in 2015, where we started getting interested in battery storage, noticing the potential for it. And so we actually commissioned some research to be done by Michigan State in 2016, and that was done for a couple years and led into our first few battery projects. And even backing up before that, we realized the energy landscape was changing and that your traditional model may not be effective for the future. And so it's one of the things that when for 7 years, I was involved in recruiting for interns and full-time hires at Consumers. And I would often talk about the exciting nature of the energy industry right now, and that it's the most exciting time to be involved in the energy industry. We have to, of course, compete here in Michigan with the big three and the auto industry, which is very sexy and fun and everything. But what we've been doing is painting this picture of all the excitement in energy, all the technology that's being introduced, all the decisions that have to be made so that we can make a big impact on our customers. So anyway, again, 2015, started thinking about battery storage, did some research, and then our first battery project was actually the Parkview Battery Project in Kalamazoo, and the Circuit West Battery Project that I'm presenting on today is actually our second one in Grand Rapids. So I'm going to walk through that real quick. So again, this slide just is showing how that we at Consumers are seeing the energy landscape changing. Here you obviously don't see any big central-based generation. We got batteries, solar, wind, all interconnected with a city and distributed across our service territory. So apologize, this might be a little bit small for those of you in the room, but this is our Circuit West project. It is basically what we're calling like a learning laboratory. We're putting a lot of technology into this area and trying to see what benefits we can derive on our grid. It's composed of three main parts. It has distribution, where we've installed a lot of automation, so automated switching. In the event of an outage, switches can operate automatically and isolate that outage and get the other customers back online. It has a rooftop solar project where Consumers owns the solar and they installed it, and we're going to operate and maintain it on the top of somebody else's building, so that was a first for us. And then we saw the opportunity here, because we were putting all this technology in here, let's put a battery in here as well to try to see what type of benefits we could derive from it at this location. And by the way, this is in Grand Rapids by 131 and 196, if you're curious. So the Circuit West battery, it's a half megawatt hour. It is a lithium-ion battery, an NMC nickel manganese cobalt battery. Operating modes, so we have several different operating modes on there. Solar smoothing, power factor correction, frequency regulation, peak shaving, and voltage regulation. And again, one of the reasons for the multiple operating modes is, of course, we want to be able to value stack, but also because we're trying to learn about all these different things. We want to learn, okay, how does solar smoothing work, and what type of impact does it have on the grid? Some notable things. Like I said, this was our second battery, so we actually learned quite a bit with our first battery. And one of the reasons why we wanted to install our first two batteries was that we wanted to start learning about the processes of installing these batteries. How do you integrate it into the utility? And I love all the research that's being done and the white papers that's being produced, but there's nothing like a real project to make you have those painful conversations about how to figure out how to do this at the utility level. And so with our second battery, we actually were trying to differentiate ourselves from our first battery. And so we designed this one for expansion. So we designed it in a way that we could easily double the size of the battery if we chose to do that in the future. Again, trying to have some flexibility with our options here. We actually have two controllers at this battery. So I don't think we've talked about it too much today, but all batteries will have some type of a controller that's going to control the output of the battery. This battery actually has two controllers, which allows us to run multiple modes at the same time. So typically, you're just going to run one mode at a time. But this, with two controllers, allows us to run two modes at one time. So that's kind of another thing where we're trying to push the envelope a little bit. No fence. So we decided in this case that we were going to try to install the battery without a fence. And we worked with our vendor to make sure that that was going to be safe. and that could look like any other piece of distribution equipment. So we have pad-mounted transformers and switches that are located all throughout our service territory, among where our customers work and live. And we decided we wanted to try to see if we could do that here, and we did successfully. Plug and play. So I know a lot of folks at Consumers will cringe when I say that, but essentially we were trying to look for a solution that was pretty much already engineered and that we would not have to do a bunch of custom engineering for the battery itself. So on our first project, we elected to do a lot of custom engineering. We set for some performance characteristics, and then we worked with our vendor, and everything was custom engineered right from the beginning. In this situation, we said, okay, we want to buy a product that's pretty much already there, and we just have to figure out how to plug it into our systems. So we learned a lot from that. And then the last thing that's notable about this project is that we set it up in a way that we could potentially use it in an islanding scenario in the future if we chose to. So we're not making that decision yet. I'm not committing to that today, but it is something that we're very interested in. And so we set this up in a way that we could use it like that in the future. So again, with this project, we're really trying to build in as much as we could in terms of learnings from it. So getting into a little bit of the construction of it, this is the piece of property that we got. It's a very, very small piece of property, so we had to be pretty creative in getting our system put in there. You can see the red bounded areas where we is our piece of property right next to a railroad, pretty congested. This is a rendering that we put together for the RFP, kind of shows what we thought the site would look like. I put this slide in there just to remind everybody that even though batteries are very exciting, you still got to figure out how to get them installed, and you're going to run into the same issues you do on any other construction project. So we ran into all kinds of issues installing our foundations, big problems with that. So just keep that in mind when you're installing your first few batteries, that just because it's a battery doesn't mean you're not going to have some of the same issues you do on a normal project. This shows some of the foundation construction, and we got the picture in the lower right-hand corner is showing what a vendor would call a pad-ready site. So this is something we've learned, is that some vendors, you can do an EPC where the vendor takes care of everything, build transfer, or however you want to do it, or some vendors might be interested in you providing a pad-ready site. So you provide a site where they can just plop their battery right there. So there might be some advantages to doing it that way versus having the vendor take care of all that construction. Some more pictures of delivery of the battery and what it looked like installed. We were installing this in December of this year, so that was interesting working with the cold temperatures. I don't think there's anything notable there. This is a picture of the site as it was finished. As I said before, we had two controllers, and you can kind of see the configuration set up we basically have two batteries, two inverters, so it's set up to be able to operate in those two different modes. This shows a little bit, just very basic one line, very, very basic one line. Just showing basically we got our step-up transformer, which has a metering on it, going to our main breaker, which then goes to each converter, and then to the batteries, and then we have a communication system as well, so that we can communicate with the battery. This is getting into a little bit of the guts of the battery. This particular system has 4 bays. It have you can just use 2 bays. You can fill all four. We decided to fill all 4 bays. It has a HMI, so human machine interface, which is basically a touch screen, and that's what you can use to operate the battery and work on the battery and change things on the battery on site. You can also do that all remotely as well. This shows what one of the racks would look like. It holds all the battery modules, and each of these has a battery management system that will look at each one of those modules and monitor the health and the integrity of the system, and also feeds a lot of information back to the controller that we then actually have access to as well, so we can really see how the system is operating. This shows the fire protection system. So we are very interested in this, obviously, for obvious reasons. This has Novak system that will operate if it detects heat, and it basically releases this gas which extinguishes the, displaces oxygen and distinguishes the fire. This is getting in, again, a little bit more technical here, but basically a one line showing how the battery is configured. We have our utility meter. We have a couple system meters. We go through an AC disconnect and then into our PCS or inverter. That is connected to the batteries, as well as the controller is connected to everything as well. We have HVAC on the system. That's very important to keep your battery system at a temperature that you want it at. So some integration challenges. So change management is really important with battery storage. In some ways, it's very much like the other things that we've seen before at a utility, but in some ways, it's very, very different. And so you have to be cognizant of that as you're installing it. Distribution versus generation asset. So batteries are very different because they can be a source and they can be a load. And so we've really struggled with that, not only on the accounting standpoint, but also the operations and maintenance standpoint. Who operates and maintains these things? Are they a distribution or a generation asset? Very big challenge that you have to go through. Where we kind of landed on that was that we wanted it to, whatever the primary function of the battery was, that's the asset that it would be. So if it was primarily being installed for power quality purposes on a distribution circuit, it's going to be a distribution asset. If it's primarily going to be installed to serve the market, it's going to be a generation asset. Control and monitoring, again, trying to figure out how to control and monitor these things. They are different than other systems that we have because there's so much power that you have with a battery. There's so many different options, configuring operating modes, prioritizing operating modes. So that's a big challenge. I already talked about operation and maintenance. IT challenge. So with the two battery systems that we bought, our vendor wanted to have eyes on the system, and so we had to provide them a live feed, basically, of the data from the system, and that posed some pretty unique IT challenges to get that set up in a secure way. Just something to remember when you're doing your project. And then where should we put our next battery? So it's already been touched on a little bit, but the planning for your next battery is a big challenge because your distribution planning folks don't always work with the generation planning folks and the IRP. And we already heard about how the IRP is generally it's generation focused. And so where to put our next battery, that's kind of something that we have to develop, that relationship between our distribution and our generation, because it is such an interdependent relationship when you're talking to installing batteries. So that's something we're working through now. And then lessons learned. Education of the workforce is key. I found that in my project meetings that if I took more time up front to explain the project, especially the folks that had just kind of come on board, everybody wasn't on board right at the beginning of the project. If I took more time up front to explain the project, it would really help out with the execution of the project. So take that extra 10 minutes and give the history of why we're doing this and some of the background, and that would really help because, like I said, it's pretty new in the utility industry. There are parts that are similar to what we've done before, but when you're starting to talk about the operating modes and all the different things that this can do, we have pieces of equipment that can do most of what a battery can do, but they're all kind of individual pieces of equipment. Here on a battery, you have a piece of equipment that can do 17 different things, and that's quite a bit different. So take the time to educate your workforce when you're going through these projects. Schedule. So getting a new contract with vendors that you haven't worked with before. We didn't put in enough time for that. Battery vendors versus the utility. So we notice here that some of the battery vendors that we worked with, their contracting strategy was a little different than we'd seen before, so that's something to take into account. Custom versus plug and play. Again, I already kind of talked about that. The custom solution is going to take a little bit longer, but it's going to be customized, obviously, to your needs. Plug and play is not going to, you're not going to necessarily get all the bells and whistles that you might want, but it's also going to be a lot quicker. Black box strategy. So this is a strategy that I took with this project, is that I said I wanted to be agnostic to everything that's really inside the fence. So I want to focus on what we are good at as a utility, which is the interconnection. We're good at interconnecting. We have to figure out how to meter this thing, how to plug into it really well. And so I would recommend this strategy for the first few projects that you take, because you focus on the things that you're really good at and that you have to execute well on, and put in the performance metrics into your contract with your vendor to make sure that they are handling everything in the box correctly. And then fence versus no fence, we actually, like I said, we pushed the boundary there, and we didn't put a fence around our second battery. We found some challenges with that, where the vendor actually had a couple switches and things on the outside of the battery that we ended up having to go back and retrofit and cover to make sure nobody got to operate them. So that was another lesson learned that we had. All right, and then I'll stand for questions. Thanks.
Thank you. Had a lot of questions come in, as you can well imagine. And I'll just start firing them at you. And I guess I'll go down the line. We have a good 15 minutes, and I think the break, we butt up to the break, but that's negotiable, I've heard. Although I have a meeting, so I don't know. Maybe I'll cut it off. Kate, what is Invenergy's levelized cost of storage?
That's a good one to start it off. I don't really have an answer for that, just because our projects have been so different, especially lately. So it's really hard to compare apples to apples. I think that cost is going to change with a bill transfer versus a PPA. And if you're stacking functions, you obviously have to do a lot more work up front and make sure that all of the major equipment can perform to those functions. And in a lot of cases, that's a question for what kind of inverter you spec. I know this isn't the answer you're looking for, but we see typically energy storage costs from our suppliers around in the upper 100s per kilowatt hour. So we could say 180 per kilowatt hour or so, and then from there we pile onto that for our construction. And I really can't give you a better idea than that.
Well, that's pretty good. Thank you. Roman and Tim, are there abandoned mines in the Lower Peninsula suitable for pump storage?
Probably. No, there are. You might have noticed on the map, there are a bunch of mines. We just don't know anything about them yet necessarily. But as an example, anyone know where there's an abandoned salt mine or a big salt mine in Michigan? Mm-hmm. Under Detroit. Yeah, not bad, huh?
Catherine, is there a harmonized user experience dashboard so each customer can see their usage, but your company can see all the systems as a portfolio?
Yes, we do have that. But we are also the owner of a lot of the systems. So the flywheel and the compressed air, the two projects that I talked about most, EnerStore actually owns them. So we don't, there isn't a customer per se, other than our contract with the IESO, the system operator. And yes, the system operator can see how the facility is performing and see its statistics, and they also keep track of their own statistics for it too. But yes, for each one of the batteries that we have behind the meter for the commercial customers, yeah, they have their own ability to see how it's performing, and we also have access to that. So yes.
Thank you. Nate, when you talked about what next, where to deploy the next battery, I know Consumers is starting an initiative kind of to look at it from a company perspective. Batteries may be installed in a customer's home where they rent it, kind of like they're doing out east. Do you have any comments or thoughts about that and whether that might be the next battery or where?
Yeah, we are looking at that, and I'm not sure how much I can comment on it. So
Okay, sorry.
No, that's okay. What I will say is that Consumers is very interested in all types of arrangements. So whether it's in front of the meter, behind the meter, whether Consumers owns it or doesn't own it, we're very interested in all the ways that battery storage can serve a purpose. And so we are looking at that one specifically, and I'm sure we'll be learning a lot from it when we go through that project. But yeah, we see a ton of potential and just trying to figure out what's the right fit. I mean, we're not there yet, but we're open to everything, I would say.
Okay, thank you. Kate, is Invenergy's choice of an LFP technology based primarily on cost, safety, or other factors? And have you considered lead acid batteries and why?
Yeah, it is primarily based on cost and safety. So to give a little bit of background for those who aren't familiar, there's many different types of lithium ion batteries. The two main types are lithium iron phosphate and nickel manganese cobalt. Lithium iron phosphate, or LFP, has a broader temperature range that it can operate in. So maybe it's something like, maybe it can operate down to 15 degrees Celsius and up to, I think, like 45 degrees Celsius. So when you're talking about climate control in your building or in your container, it's a pretty broad range. Where NMC, I don't actually know that temperature range, but I know it's more narrow. So just inherently there, you're going to have to spend more money on your HVAC system and your controls. You're going to have to run your HVAC system a little bit more so you have more aux load through the year. So that's something that we definitely consider. LFP is also just sort of a little bit safer of a technology to operate. We have looked at lead acid. So we have that project in New York that is, a very long duration project. For the microgrid portion of it. So we've looked at lead acid for that one. We continue to sort of compare costs there. A lot of if we were ever going to do any sort of ancillary services in addition to the microgrid capability, we would probably not use lead acid. Lead acid doesn't like to be cycled a lot. Lithium ion is fine with being cycled a lot, so you can see how that could limit your sort of ancillary services that you might want to provide.
Thank you. Roman and Tim, what environmental remediation would have to occur before using mines as pump storage?
Fantastic question indeed. That would be site-specific, and that is why one of the reasons why we got that specific request from our funder to look at the water quality was actually prompted by sort of concerns over environmental conditions of the propellant to be used. So yeah, it will be site-specific. There are sites that, in my view, will not require much. And there will be sites that maybe saw a recent post-industrial use, and whenever you have the use of solvents or oil potential spills, that kind of stuff, you will need to sort of then the remediation would have to be both surface and surface would be obviously one of the things that will need to be taken care of in addition to looking at the mine water.
Yeah, and just to follow up, a mine is not a mine is not a mine, right? That acid mine drainage may be a problem for some kinds of mines. They're not in our area. Most of the environmental concerns about the mines in Upper Michigan are from the processes that occurred at the mill and after, rather than the mines themselves. But again, it's a question of whether you want to look at this problem holistically from the standpoint of the community that lives around that mine site, or whether you want to look at it from the standpoint of the installation of this technology.
I'm going to fire off another question at you two. What capacity megawatts is being considered in this underground projects, or is it yet to be determined?
The correct answer is TBD. This is very, very preliminary. So we are. My colleagues, because I'm not an engineer, they're looking at, in terms of energy, they're looking at 150 megawatt hours. In terms of power, they're looking up to 150 megawatt hours, and in terms of power, they're looking at up to 50 megawatts. So, and it's just one mine that we're currently looking at. So, obviously, both will be determined. I mean, the biggest sort of variable right now that we're looking at is basically the capacity of the reservoir, the upper reservoir, right? So everything else will be determined by sort of the suitability of a particular hydroelectric turbine, the number of hydroelectric turbines, and obviously that can be driven by the intended use, what this facility should be used for predominantly. So that's where we're at, but stay tuned.
And actually, this is just for my clarification. Your study is going to look at Quincy Mine specifically in the task, or is it the nationwide survey?
So, unfortunately, we will not be able to look at Quincy Mine in detail. We looked at it preliminary to sort of, when we have this idea, when Tim and I had this idea, we promptly liaised with engineers who actually were determined to put us back in our places, respective places. But once we actually had this conversation, they got excited as well. So we haven't been proven wrong yet. So we've done the preliminary sort of stuff. The preliminary analysis occurred on the basis of Quincy Mine. But the current site is in Nagani. It's a Mather B mine. So we are one site. We're bound to one site. The idea is to take the findings from this site, apply it to the extent possible, or to the extent possible within our budget, right, to a more broader assessment. But the idea behind sort of what we would like to be doing is doing this kind of assessment on the national scale. So that's the sort of the final. This is where we would like to be. This is the goal, to do it on the national scale.
Thank you. Catherine, what is the round-trip efficiency for the Godrich project, and what are the main applications?
Yeah, for sure. Okay, so this was something that I would have loved to talk more about, is just the different applications for different types of energy storage. Compressed air energy storage is a long duration, high energy storage technology. So the dollar per kilowatt for compressed air energy storage is very low, but the dollar per kilowatt tends to be pretty high. So you want something that that has, similar to the pumped hydro that you're looking at, something that has a very long duration. So for us, our demonstration project in Godrich is only 4-hour duration, but in the that would be about 8 hours or even more longer for duration. So this is more of that bulk energy storage that is filling those major gaps. It's really good at doing things like wind integration, trying to level the output of a wind farm, or doing the larger differentials throughout the day for energy storage. In terms of efficiency, when you look, so efficiency is really interesting when it comes to energy storage. Some projects are very dependent, like economically dependent on the efficiency, the round trip efficiency, and others it almost doesn't matter. And generally, the longer duration energy storage project you have, the less the efficiency matters. That's just a trend that we have noticed for developing multiple types of energy storage projects. So compressed air energy storage in general does not.
Just loudly, they're all starting to die, I think.
Oh, okay. I am really loud, so I could do that. The compressed air energy storage in general has a pretty low efficiency, 60%. So you lose about 40% of the energy that you put in. You would think that's crazy. Like, why would you bother doing that? Why bother storing the energy if you're losing that much of it along the way? But it really does make sense. The fact that the storage, $1 per kilowatt, is so cheap because it's so easy to make these caverns so big that, and when you're taking the off-peak energy, the value of being able to actually time defer that energy from when you take it off and put it back on the grid makes it economically possible. We wouldn't have built this if it wasn't economically possible. I'm a project developer, So anyway, 60% is about that's about what compressed air energy storage is. For comparison, batteries tend to be in the mid to high 80s. For energy storage. Flywheels tend to be in the mid to high 80s. But you can't get that cheap on $1 per kilowatt hour when you look at those technologies.
Thank you. Nate, what is islanding potential, and why would consumers be hesitant to commit to it?
So islanding potential. So when we look at like a microgrid or an island, it usually has several different parts. It's going to have some type of generation, so probably renewable generation, which we have that at Circuit West and rooftop solar. It's going to have a battery. Generally, it's going to have some type of diesel gen set, so a diesel generator as well. And it has some type of controller that is going to control all the systems and make sure they talk to each other. It's also good to have some automated switching in there if you can, to help out with the islanding. And so at Circuit West, we have the battery, the solar, and the automated switching. We don't have the controller, the main controller that controls the whole system, and we don't have any like diesel generator in there. But that's what I mean by islanding potential. We have 3 of the maybe 5 components that you need, and so we see this as a potential for doing an islanding pilot if we wanted to do it there. The reason we're hesitant is not that it's not something we want to do. We absolutely want to island a battery, but there are some challenges, technical challenges. So our whole system, and I'll try not to get too far in the weeds here, but our whole system, or most of our system, is protected by devices that rely on fault current. And so they rely on, if there's something on the line or line drops on the ground, there's all this surge of energy that goes through there, and that burns up the fuse or blows your breaker. Well, the problem with batteries is that you're limited, right, on how much power you can put out there. And so there's this inherent technical concern that we have on making sure that whatever we do, can we use our existing systems that are in place to protect the system? And so we're kind of in the process right now doing research on that and figuring out how to do it. But so it's not that we're hesitant. We're very excited about this opportunity and this potential, but we want to make sure, obviously, that we do it in the right way and in a way that protects the system. So that's why we're holding off for right now.
All right, thank you. I was mistaken. I thought we had a longer networking break. It's actually just like 3:20 now to 3:30, so I am going to break off. We do have, unfortunately, a bunch of, go ahead.
Sorry, I just wanted to let everyone know, give you my sincere apologies, but Roman and I both have to drive to the thumb of the upper mitten today because we teach early tomorrow morning. So we are going to be leaving after this conversation. And it's not that we don't find everyone interesting. We want to know more about what you're doing or network more, but we really do have to go. But we will. He'll drive. I'll watch Twitter if anybody wants to shoot us a question. But thank you very much.
Please join me in thanking this awesome panel.